Well, so today we'll move on to another section, 7.4, integration of rational functions by partial fraction decomposition. Well, so partial fraction decomposition is a topic that you may or may not have studied back in pre-calculus. So in case you didn't, well, I'm going to go over the whole process, all the details, all the guidelines to perform such decomposition. Well, no, but before doing the partial fraction decomposition, let's first of all see where is this really coming from. Well, back in intermediate algebra, you were asked to compute this kind of operations with fractions. Well, and this relies even backtracking to for example, 1/2 plus 3/2. To combine fractions together, well, we may go ahead and combine these fractions together when we have the same denominator, keep the denominator, and just do the actual operations in the numerator. That's 1 plus 3, that's 4 over 2, and that reduces it to 2. But in the case 1/3 plus 1/2, we cannot just add the fractions together like this, because in this case we have different denominators, and in the previous example we have the same denominator. So whenever we have the same denominator, do the indicator operation with the numerators, but before doing that, make sure to have the same denominator whenever you have different denominators, and find an LCD in this case. So, well, in this case, that's going to be a 6. 1 times 2 is 2, plus 3 times 1 is 3. That's 5 over 6. In the same way, we handle rational expressions or fractions, but in this case, involving variables. So we're going to do the same. Now, when we look at these expressions right here, we can actually tell that we don't have the same denominator, because one denominator is an x minus 3 and the other denominator is an x minus 2. So we need to make sure that we have the same denominator, and in this case we're going to, let me rewrite it again. I'm going to leave a space for something you'll see. And well, we need to get a least common denominator. In the same way that we multiply by 2 and divide it by 2 for the 2/3 in the numerical example, I'm going to multiply by the factor that makes them the same. X minus 2 and x minus 3, x minus 3. Well, now that we have the same denominator, notice the same denominator will be x minus 3 times x minus 2, and in the numerator all we do is leave the indicated operation. That's going to leave us with a 3 times x minus 2 minus 2 times x minus 3. All we have to do here is focus in the numerator, distribute, and that's going to give us 3x minus 6 minus 2x, negative times a negative, careful, that's going to give us a positive 6, and we'll just keep bringing that common denominator, x minus 3, x minus 2. Alright, so well, what are we going to get from here? Number one, so check how these 6's cancel, and 3x minus 2x equals to simply x over x minus 3, x minus 2. Well, that was the typical problem back in intermediate algebra, and you may have to do this a few times back in calculus 1 maybe, and back in pre-calculus as well. Alright, now partial fraction decomposition is basically doing the reverse of what we just did here. So now in this topic, we're going to be given a compressed fraction, a one big fraction, we need to break it up into simpler fractions. Okay, that is partial fractions. Now, and in this case, well, we do this in order to integrate simpler terms instead of trying to integrate a crazy expression like that. Now, how do we go about the partial fraction decomposition? Let me do one example. So let's decompose x over x squared minus 5x plus 6. Well, number one, well, this is already one single fraction, so how are we going to get partial fractions from here anyway? Well, number one, what you might want to do is factor out the polynomial in the denominator. So in this case, well, because it's a trinomial and the leading coefficient is 1, we may just go about the double bubble method. And all we need to do is find factors of positive 6 that add up to negative 5. What are those factors? Negative 3, negative 2. Negative 3, negative 2. Don't forget the x in the numerator. Well, that means we have two factors. Each factor will correspond a partial fraction in the following way. A over x minus 3 plus b over x minus 2. What do we do with the x? You might ask yourself, what do we do with the x right here in the numerator? Just ignore it for now. Okay, just ignore it for now. We're going to use it when we find these constants a and b. Okay, well, so how do we find these constants a and b? Well, you know these two from the previous problem, right? Because we already did this backwards. But okay, let's start where we don't know what a and b are. By guess and check, and then okay, let's put random numbers and do the sum of the fractions. Well, that's going to take forever. That's not an efficient way to do it. There is a natural process for this. Well, and what we're going to do is repeat. I'm going to write these two separately and treat it like an equation, because what are we doing here? We're given this crazy equation, right? This crazy expression. We're doing some algebra. We're following the line until we get to the final answer. But well, in the meantime, I'm going to treat these two steps as one single equation. X over x minus 3, x minus 2 equals a over x minus 3 plus b over x minus 2. Well, so we're going to use this equation to find the unknowns a and b. However, this equation is too ugly. So let's make it look nicer. And by making it look nicer, we mean to cancel out or to kill off these denominators. You'll see. Well, how do we get rid of these denominators? What would you do?
Multiply the x minus 3, x minus 2 both sides.
Exactly. So what we do in this case is multiply both sides of the equation by the least common denominator. What's the least common denominator? The least common denominator will be an expression that will divide out both the x minus 3 and the x minus 2 at the same time. Okay? And in this case, the product of these two factors, x minus 3 times x minus 2, will do the work for us. So let's see. Distribute and check what's going to happen here. Both factors are going to get canceled out, and that's going to leave us with x equals. Let's do the distribution over here and check this out. When we distribute this, no, that's the lowest. Okay, when we distribute this x minus 3 times x minus 2, wait a little bit. Okay. See how the x minus 3's get cancelled, leaving it with the product between a and x minus 2. You guys following me here? Okay, so a times x minus 2. And then when we do the distribution over the second term on the right hand side, see how the x minus 2's cancel leaving us with b times x minus 3. Alright, well, this is a simpler equation. This is the equation that we use to solve the problem. And we're going to call this our basic equation. Alright, that's our basic equation. We're going to use this to figure out the values of a and b. But well, the problem seems to be more complicated than we actually thought, because what do we have here? We have one equation and three unknowns. If we had three equations, three unknowns, use your favorite method to solve systems of equations with three unknowns. Elimination, some kind of substitution, matrices, RREF on your graphing calculator, but well, this is only one equation, so we need to find an alternative to solve for this equation. How do we do this? Well, number one, so we need to think of clever numbers. So I'm going to think of a clever number to zero out one of the terms. For example, to zero out the first term so we can calculate b, and another clever number to zero out the second term right here so we can find the a. Okay, can anyone think of one of those clever numbers that's to zero out? 2. So how about for x equals to 2? Alright, so number 1, so 2 equals to a times 2 minus 2 plus b times 2 minus 3. We'll write those 2's. So what's going to happen here? This one goes to 0, and oh, we're going to be able to find the value of b. So this is going to be 2 equals to b times 2 minus 3. Isn't that going to be a negative b? And that means b equals to negative 2. So that's the first calculation. So no need to solve a system of equations, and in fact there's no way we can find another equation. That's only one equation with, in this case, two unknowns. Well, technically x is a variable, but actually we use x as a starting point to find a and b. Okay. Can we think of we already found b, we need to find a. Can we think of a clever number to get a? X equals to 3. So for x equals to 3, well, so that's 3 equals to a times 3 minus 2 plus b times 3 minus 3. And check this out. The b term will get zeroed out, and we will be able to find the value of a. So 3 minus 2, which is 1, that equals to a, which equals to 3. Oh, no need to do anything else. Alright. So we found the constants a and b that give us this partial fraction decomposition. So let's just go ahead and plug them in where they correspond. So 3 over x minus 3 plus negative 2 over x minus 2. But well, let's clean up the signs right here. 3 over x minus 3 minus 2 over x minus 2. Isn't it the same as the given expression that we got? This one right here, it's the same. But we're going back and forth between combining fractions together. We combine the fractions together. Now we did the reverse, which is break it up and get exactly the same. So this is what we're going to be doing for the entire week, partial fraction decomposition. All right. Okay, so let's do one example in which we will integrate a function like this. So integration using partial fraction decomposition. They're asking us to integrate x over x squared minus 5x plus 6. Well, number 1, use substitution, which is what you want to try first. X squared minus 5x plus 6, and du equals to x minus 5 with respect to x. Well, we only have the x. We could add the minus 5 and then get the 2, but that's just going to be too messy. So just leave. So in this case, it's not going to be pretty. It's not going to be fun. So, well, in fact, for this particular example, they're asking us to integrate the same expression, the same function, for which we already did the partial fraction decomposition of. So for this example, let's use this result and integrate. Well, so that's going to be the integral of 3 over x minus 3 and minus 2 over x minus 2 with respect to x. Well, so how about we split this into two integrals? 3 integral of the x over x minus 3 minus 2 over times the integral of the x over x minus 2. Well, these are two very simple integrals. I mean, don't even need to show the u substitution because I'm the u du part. So for integrals like this, recall you can just go straight to the final answer. So that's going to be 3 ln x minus 3 minus 2 ln of x minus 2 plus c. And that's final answer. Yes?
Can we combine the logarithms?
You can combine the logarithms. You're not required to do that, but if you want to do them, that's fine.
So that would be one giant.
It could be, yeah. So if we use, for example, in this case, the basketball rule for both of this, that'll be, well, ln of x minus 3 cubed minus ln of x minus 2 squared, and then using the minus, which is the quotient, that'll be ln of the quotient x minus 3 cubed over x minus 2 squared plus c. But no need to compress them into a single logarithm. This is just leaving them as a sum or difference of individual logarithms is more than enough, especially because some of the exercises for partial fraction decomposition, the integration or just obtaining the coefficients a, b, c, d, you know, we're going to do one with 4 later this week, is going to take forever, and then from there having to do all this, just forget about it, right? You're not required to do that. All right, so on the next page here we have the steps to decompose this big fraction into a sum or difference of partial fractions. Well, so it all stems from the fact that we may have improper and proper rational expression. Number one, first of all, let's go back to the definitions of improper and proper fractions. So what's an improper fraction in numbers? Forget about expressions of x. Just give me an example of a number, of a fraction that is proper. 2/3. All right. Why is 2/3 a proper fraction? Exactly. The numerator has to be smaller than the denominator in order to call it a proper fraction. Well, what about 7/4? Is that a proper or improper?
It's not proper.
It's not proper. It's improper in this case. And further, we need to write this as a mixed fraction. Well, not all the time, but we will for these expressions. And well, 7/4, that's a 1 and 3/4. That is essentially quotient plus remainder over divisor. It's important to start bringing this back to the conversation because we're going to use it a lot when we do polynomial long division. Another one, okay, 5/5. What's this? Improper or proper? I hear a combination of improper and proper. So it's improper because the definition is that a proper fraction is either it's just less than the denominator, and improper is whenever we have the numerator to be exactly the same or larger than the denominator. So how is that going to be related to part to part to fractions actually involving x as well. Let me write down these definitions here. So, proper whenever the degree of the numerator is less than the degree of the denominator. But improper whenever the degree of the numerator is greater than or equal to the degree in the denominator. Alright, so that's how we make a distinction. So in just numbers, the numerator is a smaller number than the denominator in order to be a proper fraction. In expressions of x, we don't go with the numbers because that's no longer just numbers. They also involve x. In this case, we'll look at the degrees. And same, degree is less than the denominator and the numerator, well, that's proper. So that's the first step in the case that we have an improper. Second step, factor the denominator. And in this case, you have to be fluent with all the possible factoring techniques. Special products, perfect square trinomials, like the one we did in the previous exercise. Trinomials in which the leading coefficient is different than 1. There's plenty of ways to factor those. There's plenty of shortcuts to factor those. What else? Differences of squares, sums, or difference of perfect cubes, etc. Pretty much every single factoring technique. What else? Factor by grouping. Factor by grouping might be one very, very useful. Well, once we factor our denominator, let's write out our partial diffraction decomposition with unknowns A, B, C, D, E, F, well, as many letters as we need. Okay? In the previous example, we did one with only 2. Now, here is the thing. Whenever we have linear denominators, the numerator in the fraction has to be a constant. I'll explain why in a minute or later. If we have repeated linear factors, you might want to highlight this part. If the factor is linear and the numerator of the partial fraction is a constant, if repeated, then we need different partial fractions for its power. That's something I would like to cover more in detail maybe next time, maybe not today. And in the case in which the factor is quadratic, and by quadratic we mean irreducible quadratic. Because of course we already did one with a quadratic polynomial in the denominator, but that quadratic polynomial in the denominator was reducible to a product of two linear functions or two linear factors because it was factorable. So and there will be trinomials or even binomials that are quadratic that we won't be able to factor over the set of rational numbers. In some cases, well, you can still factor it out over the set of imaginary numbers, but that's not our class. That's something that you will use later in your courses in differential equations and complex analysis for those of you who are electrical engineering majors, civil engineering majors who will work with those complex valued functions. But that's going to be later. For now, we're just going to limit to work with rationals only. Okay, so let's look at one example alongside with the checklist that we have here. Okay. Number 1, let's integrate 2x minus 1 divided by 4x squared minus 9. Number 1, is that rational expression in the integrand a proper or improper?
Proper.
It's proper. Do we need polynomial long division? We're good then. Okay, the next step, factor the denominator. Oh, well, number 1. It's do you guys recognize the form? Difference of squares, so you might want to factor this as 2x minus 3 and times 2x plus 3. Okay. Well, now that we have the factors, the two factors, let's split each factor into a partial fraction. That is the integral of a over 2x minus 3 plus b over 2x minus 3, or plus 3 rather, with respect to x. Alright. And well, how do we move on through this problem? Well, let's go back and let's actually set the quantity in the previous step equal to the quantity in this last step. Set it up like an equation, simplify the equation in order to find those constants a and b. So let's write 2x minus 1 over 2x minus 3, 2x plus 3, equal to a over 2x minus 3 plus b over 2x plus 3. Alright, let's multiply both sides. So to simplify this equation again, let's kill off the denominator. And in order to accomplish that, multiply both sides by the least common denominator. That is the expression that will divide out both the 2x minus 3 and the 2x plus 3. And in this case, it happens to be the product of these two. 2x minus 3, 2x plus 3. 2x minus 3, 2x plus 3. So, well, check this out. Check what's going to happen. When we distribute on the left hand side, both factors are going to get divided out, and that's going to leave us only with a 2x minus 1 equals, okay, let's do the same over the right hand side. So when we distribute 2x minus 3 times 2x plus 3, see how the 2x minus 3's cancel, leaving us with a times 2x plus 3. And lastly, do the distribution over the second term on the right hand side of the equation and see how the 2x plus 3's cancel, leaving us with the product between b and 2x minus 3. Up to this point, you guys following me here? Is it making sense? Okay, so this is a reduced equation. This is what we call our basic equation. And this equation, we will use it to find the constants a and b. But again, we already discussed that we have essentially one equation and three unknowns, a, b, and x. But we only care about a and b. We don't care about x. We're not getting a numerical value for x. So, here is where we use our number sense. So, can we think of a clever number that will cancel one of the terms? Let's say the term containing the a or the term containing the b, so we can find either one. How about negative 3 halves? Like that, for x equals to negative 3 halves. So this is what we do. So 2 times negative 3 halves minus 1 equals a times 2 times negative 3 halves plus 3 plus b times 2 times negative 3 halves minus 3. Okay, so negative 3 halves, negative 3 halves, and negative 3 halves. Let's do the arithmetics for this. So number 1. Okay, the 2's cancel here, leaving us with negative 3 minus 1 equals a times, cancel the 2's, that's going to give us negative 3 plus 3. And on the second term, b times, cancel the 2's, negative 3 minus 3. Well, negative 3 plus 3, isn't that going to be 0? Which actually zeroes out the first term, leaving us with negative 3 minus 1, isn't that a negative 4? And b times negative 6, or negative 6b. Then from here, just divide both sides by negative 6. b equals to 2/3. So that's the first constant. That's constant number 1. We just figured that out. Now, Number 2. Can we think of another clever number that will divide out, or rather cancel, one of the terms, so we can find, well, in this case we figured out the value of b. Now we need to figure out the value of a. And to figure out the value of a, this time we need to zero out the second term containing the b. So what would be that number? Positive 3 over 2 this time, right? Okay, so for x equals 3 over 2, what are we going to have? Well, 2 times 3 over 2 minus 1 equals a times 2 times 3 over 2 plus 3 plus b times 2 times 3 over 2 minus 3. Alright, so that's 3 over 2, 3 over 2, 3 over 2. Let's do the arithmetics here. And okay, cancel these 2's. Canceling those 2's will leave us with 3 minus 1 equals a times, cancel these 2, 3 plus 3, plus b times, cancel the 2's, that's 3 minus 3. And oh yes, this is just what we wanted, right? To get this zeroed out so we can find the constant a. Okay, so that's going to give us, well, 3 minus 1 is 2, 3 plus 3 is 6a, divide both sides by 6, a equals to 1/3. And well, we got through what I would say the most annoying part of the problem, which is figuring out, doing all this algebra. We may now go back to the original problem and okay, let me highlight the constants where they correspond so you can see where I am going to plug this in. So a over there, okay? Well, I don't have space over here. Let me scroll this down to this is going to be the integral of a, which is 1/3, over, what was that, 2x minus 3, plus b, which is 2/3, 2 over 3, 2x plus 3 with respect x. Well, so from here, let's just write it as 2 separate integrals. Number 1, I'm going to write it as 1/3 integral dx over 2x minus 3 plus 2/3 integral of dx over 2x plus 3. All right. Well, I think these two integrals are simple to evaluate, so no need to show me the u du. I'll explain. I'll elaborate on that in a second. So here I'm just gonna go like 1/3 space ln of 2x minus 3 plus 2/3 space ln of 2x plus 3. What's the space for? The space for is for that factor that comes out of the integration. In this case, it would be a really baby u substitution. That'll be a 1/2. That'll be another 1/2. Okay, so that's going to be plus c, of course. This will be 1/6 ln of 2x minus 3 plus, cancel these 2's, that's 1/3, 2x plus 3 plus c. Final answer. Yeah, the logs together and having radicals with an index 6 and a radical with an index 3 in this case. So, but again, no need to do all those steps. Okay guys, so for the next example, I really need to go, even though it's short, I really need to explain a few things. However, instead of going to the next example, I would like to talk about what I did to just go from the integral to the result. Again, for very simple integrals like this, no need, technically you should be doing, for example, u equals to x minus 3 du equals to dx, which means dx equals 1/2 du. This is where this 1/2 is coming from the u substitution. But again, these integrals that are really simple, you don't need to show me to show that you did u substitution. For example, another one that you don't need to do the whole thing when we do e to the, well, cosine of 5x dx. Well, the integral of cosine, isn't it sine 5x? But well, in this case we just do 1/5. Well, how can we relate these two? Well, it's the same as taking, for example, the derivative of cosine of 5x. Take the derivative of that. What's the derivative of cosine? Alright, let me do sine instead. So sine 5x, that's cosine 5x. But well, by mini chain rule, what do we do? Multiply, right? But in the integration, what do we do? Don't we do the reverse? Well, in the same way, e to the 7x dx, what's the integral of the exponential? Isn't it itself? Oh, okay, let me skip the integral. Let me do the derivative instead. E to the 7x prime. The derivative of the exponential is always itself, e to the 7x, but by mini chain rule, 7. But because the integral is the inverse operation to the integral, well, the integral of the exponential is also itself. However, in the derivative, we multiplied by this constant here. What would we do in the integration? Isn't it the division or multiplication by the reciprocal? Because that's the inverse operation of the multiplication. So in this case, this is what I did here. I just went ln of this quantity right here times 1 over the coefficient of x. Now, for example, if you have an integral that is, for example, more elaborate, say the integral of 7x to the 7 cosine of 5x to the 8th, right? Well, number 1, this is 7 integral of x to the 7 cosine 5x to the 8th dx. In a situation like this, my advice is that you show that you did use substitution, because even though it's the same pattern, 1 degree less outside, which tends the du part of the problem. This is what we did with the logs and the baby exponentials and cosine that I did before. But this is not that simple. This is a little bit more elaborate. In a situation like this, yes, show that you did use. So u equals 5x to the 8th. du equals 8 times 5, that's a 40. X to the 7 dx, and x to the 7 dx equals 1 over 40 du. Alright, so it's not that simple for this integral. It's not that simple to go, oh, the integral which is sine and like 1/2, 1/3. No, we really need to figure out this factor right here. We really need to do this derivative to write it down. Or, I mean, unless you can still do it in your head, but I still don't recommend you do it in your head, okay? And well, this integral becomes 7 times the integral of cosine of u, and dx becomes 1 for x to the 7 dx becomes 1 over 40 du, okay? And well, the rest is just, the integration. So just wanted to cover the difference between when we can just go, oh, the integral of 5x 1/50 to the 5x. The integral of 1 over 5x plus 7, ln of 5x plus 7 times 1/50. In that situation, that's fine. Situations like this, it's important it's better to show the whole du process. And the reason I'm discussing this, it's because, well, today you have an exam, and that's where you need to have a look of how much work to show. Well, and again, we go back to, well, do you have like a really simple integral? Just go with without showing the UDUs, something more elaborate, sort of over. Okay?